All right, everyone. So today we're gonna continue to the last cluster of the whole semester. So it's about how do we make inference? What is statistical inference? Right? So after this, then we basically completed the whole process, right? Of any statistical analysis process. So let's go over this process very quick. So first, anytime you're gonna conduct the research, you're always gonna have a population of interest, right? So whatever individuals you're trying to study, if you want to study human, then all human will be your population. If you want to study horses, then all horses will be your population, right? So you're gonna have a research interest. That will be your population. Most of the time, the population size is very, very big. You can't measure every individual in the population, right? Then how do I study this population? We still want to know something about this population, right? What do? We take a small portion of the population out as a sample. And here you can control the sample size. It could be something you can manage. For example, you can only choose 10 human or 10 horses or 20 bridges as your sample, right? So that will be something you can control. Then you can measure the data from the sample. You have data set collected. Then if you want to see, hey, what kind of sample do I have? Can I describe it? And we can use the descriptive statistic. That will be our exam 1 material, right? So we can describe your sample using graphic tool, and also can calculate some numerical measures. So for example, it goes through the list. We can do bar chart, a pie chart, stem plot, histogram, and box plot. We can do scatter plot as well, right? And we can calculate the mean, standard deviation, correlation, regression slope, regression intercept. Each of those, is a way to describe what kind of sample we have, right? But even though from descriptive statistic, we know exactly what's going on in the sample, but our research question is, what is going on in the entire population, right? What do we know about the population? Then what do? We need to do inference, right? And in order to do inferences, we need to learn some theories in the class as well, probability and distribution. We only going to focus on using normal distribution to do the inferences in this class. But you can use any other distribution to do inferences as well. Right, so what are the objective of this chapter? First, we need to understand what is a statistical inference. Okay, so we're going to talk about it in a little bit. Then, in this chapter, we're going to focus on a particular type of inference. We call that a Z confidence interval. Okay. Then, first we need to know, how do I know if we need to apply a Z confidence interval to solve this problem? So what are the conditions we need to know? Okay. And then also, we need to be able to, solve it, right? So here we'll be involving calculations. How do we calculate the things we need in the common interval problems? And as well as, after you calculate it, you will need to interpret the result. So for every question from this point on, I will strictly ask for a conclusion for every question you work with. Okay? So how do you interpret the process it did after it did analysis? And the lastly, we need to know a term called the margin error, MOE. And we can also talk about how do we reduce margin error. Right. So first, what's inference? Inference provides a method for drawing conclusions about the population, right? From the sample data. Okay. So think about inference is you're going to have a population of interest. There are many, many individuals in the population. So in this population, there are a lot of measures. For example, We have mean of the population. We use a symbol of mu represent. We have standard deviation of the population. We use a symbol of sigma represent. We have correlation of the population. We use symbol of rho represent. And we have regression of the population. We have two terms. One is slope, beta 1, and the other is intercept, beta 0. So all of these are a measure of the population, and they're all unknown to us. We don't know what they are, right? And they are all parameters. If you recall chapter 8, right? We have sample statistic and the population parameter. So if you want to know any of those population measures, how do we study it? Okay? So I showed you that picture a lot, right? So we're not able to measure the entire population, but we're able to manage a sample, right? If the sample is randomly selected from the population. Then from the sample, we calculate all the measures of the list over here, right? We can calculate the mean of the sample as x bar, standard deviation of the sample as s, correlation of the sample as r, regression of the sample, we have slope, b1, we have intercept, b of 0, right? So all of these can be calculated from the sample, and actually we calculated all of those measures, right? And these measures are going to be known to us because we're able to calculate them, right? And these measures are called a sample statistic. Right? So all the statistics are known to us, all the parameters are unknown. So we want to know what's going on in the population. We want to know what kind of measure will each of those population measure will be. So the process of drawing conclusions from the statistic side toward the parameter side, that process is called a statistical inference. Right? So basically, we need to draw conclusions about the population. That's what inference is. Okay? So then think about each of the population parameter. For example, if you don't know what a population mean is, sometimes we want to make estimation about it, right? So sometimes we want to do an estimation of a population parameter. So we don't know what it is, but it's probably going to be, around here, right? So this process, we use common interval to achieve. Okay, so we use common interval to make estimations. Okay. And then that's one type of statistical inference. And then we have another type of inference. So we don't know what the population mean is, but people can make claims about it. So for example, if we say all the students at MSU is our population, I'm going to make a claim. I'm saying the average debt of all MSU students is about $15,000. So then how do we know if that claim that I made is true or false? So we need to go through a process to assess that, right? So that will be the other type of inference. Assess claims about the population parameter. Okay. Then how do I assess claims about the population parameter? That will be another inference procedure called hypothesis test. So in general, we're going to have two different types of inference. One is common interval, The other is hypothesis test. Okay. Then today we're going to start with a confidence interval. We use a short notation, CI, represent confidence interval. And in today's lecture, we're going to use a Z statistic to work on the confidence interval. So we call it a Z confidence interval. Okay. So then we use sample statistic to estimate the population parameter. Then we need to know how accurate is the estimation and how confident is our estimation. And we're able to use the confidence interval to answer, both questions. Okay. We're going to provide a confidence level. We're going to have an accurate estimation level. Okay. So also think about the process. So the inference could be any of the population measure, right? As long as you're making conclusion about the population feature, that will be an inference. But since we are an intro-level stats class, we're going to just only stay with the easiest one. We're only going to make inferences on population mean. So that means we'll either be estimating population mean, or we're going to assess claims about the population mean, right? So it's only population mean that we're interested in this class. But in the future stats classes, if you're going to take, you could be doing inferences on other population parameters, like population standard deviation, population correlation, right? Or population regression. Right? Okay. So then we're going to do Z confidence interval. How do I know if it is appropriate to do a Z confidence interval in a problem? So first you need to know Z confidence interval is a confidence interval anyway, right? So only if when you're estimating a population measure, right? So when you make estimations as a confidence interval, then we need to have three conditions. First, we need to make sure to have a random sample, right? So SRS represent a random sample. And the second, we need to make sure the central limit theorem will apply, which means somehow mean X bar will have a normal distribution. Okay? The central limit theorem is the foundation of all of the inferences we're going to talk about in this class. If central limit theorem doesn't apply, then none of our inference procedure will be valid. Okay? So that's the foundation. And then lastly, we're trying to estimate the population mean. We need to estimate it. We don't know what it is. But at the same time, we do need to know the population standard deviation sigma. So population standard deviation sigma has to be given to us. Then we can do a Z confidence interval. Okay. So then how do I do Z confidence interval? All the confidence interval will have a confidence level associated with it. Confidence level. Okay. Then for any confidence level, the construction, the calculation of the confidence interval will be, we're going to use sample mean X bar plus and minus Z star times standard deviation of X bar. Okay? So basically X bar is your sample mean, and the standard deviation of X bar equal to what? That will be from central limit theorem, right? If you think about the central limit theorem, the term here is standard deviation of X bar, right? Then for the equation, you can rewrite it. Just place sigma over square root of n of STD, standard deviation x bar. So you have a formula here, right? So this will be the formula we use to calculate the confidence interval for z statistic. So then, in the formula here, we have x bar, which is sample mean, right? Once you collect your sample, you're able to calculate a sample mean. And that's sample size, right? So that's easy to get. Once you know what your sample is, you have your sample size. And then sigma, that's a parameter. We don't know what the sigma is, but for a z confidence interval, we need to have sigma being provided to us, right? So sigma has to be known to us. That will be provided. So the only thing that's left in the calculation will be, how do we find the z star? If we're able to find the z star value, then we're able to do the calculations, right? Then how do we find z star value? So z star is related to confidence level. For different confidence level, you're going to have a different z star value matched with it. Okay? Then what confidence level are we supposed to use? That will depend on, you as a researcher. When you make estimations, how confident do you want your estimation to be? Do you want to have 90% confidence level? Do you want to have 99% confidence level? Or do you want to have 99.9% confidence level? Right? So you have to make a decision. Okay? Confidence level, basically you need to maintain at a high level so that people can believe your estimation, right? For example, if you provided an estimation, but your confidence level is only like 30%, and people will say, you're only 30% confident about your estimation. Why would I believe you? That's not useful, right? So you need to make sure your confidence level is high. Okay? The most common confidence level is 95%. And just by habit, a lot of people like to use 95%. Okay? It doesn't mean you have to use 95% all the time. You can choose your own confidence level, depending on what kind of study you're working with. Okay? But 95% is the most common confidence level, so the default confidence level in this class will be 95%. So in other words, if I don't give you a confidence level for any question, the default will be 95. So you're going to use 95 instead. Okay? So if the confidence level is not provided, so don't forget about it. Then for any different confidence level, we can find a z star. What is z star? Z star is basically a z-score from your z table, right? So that will go back to our chapter 3, right? You have a z table. So this problem, basically just like solving a lookup a z table problem in chapter 3, from any confidence level to z star, we have a relationship. Probability of z less than z star will equal to 1 plus c% divided by 2. Okay? So for any confidence level, you can find and match z star value. For example, if we do 95%, okay, then how do we find z star? We're going to write the relationship as is. Now will be 1 plus 95% divided by 2, right? Then 1 plus 95% is 1.95 divided by 2, that's 0.97. So the question becomes a chapter 3 z table lookup. With a given probability, can you find a corresponding z star? And And this is looking backward, right? From probability to z. If you look up in the z table, 0.975, you should see that the z star will be 1.96. So z of 1.96 will be what it is. Okay? So now if you look at the formula for z confidence interval, the calculation is x bar plus or minus z star times sigma over square root of n. X bar is sample mean and sample size. Sigma is given, provided, and the z star is from z table, right? And it's dependent on the confidence level, right? Then we have everything we need. We need to calculate 2 times, one for addition, one for subtraction. Okay? So we're going to have 2 numbers calculated. The addition will give you a number that's larger. The subtraction will give you a number that's smaller after you calculate, right? So then we can write our confidence interval as with a parenthesis and the small number on the left and the large number on the right and separate by comma. Okay, so that's our confidence interval. For example, if we're talking about the OMSU students as our population, and their average debt is calculated to be 12,500 and 16,000. So that will be confidence interval. Right? Then in this class, after you do the calculation, you're also required to write a conclusion. You have to write a conclusion to interpret your results. Okay? So here, the format will be, here's what I recommend you have, but you can write in a different way as well, as long as you stated it correctly, right? So here, I'm going to say we have C% confidence that population mean, we're estimating population mean for the whole process, right? So write a population median words, it will be average of the population. So population, you need to think about what your population is, right? And then that will be the average of the population is between the small number and a large number. So this is my recommended format. You just need to replace the corresponding part in quotations regarding to your subject matter. So for example, if we did a 90% confidence interval, and we find out the confidence interval is like that, our conclusion will be we have C%, 90% confidence that the average debt of the population is all MSU students, your population, right? So I'm going to write all NMSU students, and then copy the rest as between the 2 numbers you calculated. If there's a unit, write a unit down by as well. So $12,500 and $16,000. Okay. So that will complete your confidence interval. Okay. Then for any different confidence level, you're just gonna have a different Z star value to use, but the process will be exactly the same. So the textbook gave us 3 most common confidence levels. So will be 90%, 95%, 99%. So 95% the Z star is 1.960, just like what we found out earlier from Z table, right? And then the textbook provided other 2 Z-score values for 90% and 99% as well. 90% we use 1.645, 99% we use 2.576. That's the same algorithm as what we did in the Z table earlier. So if anytime if you asked about the 3 confidence levels, 90%, 95%, 99%, you don't need to go to Z table. Remember those 3 numbers. So write it down in your note card on the test. 1.645 for 90%, 1.960 for 95%, 2.576 for the 90%. And if the confidence level is any other different values, then you need to work on the process of, finding a Z-score earlier, like what we did here. Okay? So for any confidence level, work on this process. Find a Z-star from Z table. So for example, let's work on another confidence level. What if your C percent is 92%? What Z-star do we use? So we go through the process, probability of Z less than Z star equal to 1 plus C percent, 92% divided by 2, right? They can calculate 92% is 0.92, 1.92 divided by 2 is 0.96, right? So now use 0.96, look up the Z table, you can find out the Z star will be 0.96, check on the Z table, 1.75. So don't forget, you have to approximate if you couldn't match exact 0.96 on the Z table, right? So 0.9599 is the approximate probability you use to find the Z star. Okay. Then, basically just like the same process we did earlier, like here, right? You can just plug in all the numbers, do the calculations. That's how you do Z confidence. So procedure to work out confidence intervals. First, identify what you're doing. Okay, so what is the practical questions? Now, what parameters you're trying to estimate? And in this class, actually, this part is kind of skipped because we're only going to focus on one parameter, which is population mean mu, right? All the time, we're only going to focus on the population mean. So the parameter is always mean. And the plan, so once you identify the parameter, choose a level of confidence. What confidence level do you want it to be? Default value is 95%. When it's not provided, 95% is what confidence level you choose. Otherwise, just use whatever confidence level as indicated. And then select the type of confidence interval that fits your situation. So basically, we have only Z confidence interval now, but we're going to also talk about the T confidence interval. The major difference is the Z confidence interval need to have a parameter of sigma to be known to us, right? So we need to know sigma. Okay. And then solve. So basically, you have your equation, plug in the numbers and calculate it, and conclude. So basically, you need to interpret your calculation results using the context words, using the subject matter. All right, so this is our first animal for the video that will be useful for your attendance points. Just make sure you watch the video on time and answer those attendance points on time to get your attendance score. So the first picture is first animal is definitely a tiger, right? Right. So now let's work on some practices. The first practice, a researcher wants to estimate the MPG values for Toyota Camry manufactured in 2015. He randomly selected 10 vehicles from various dealers in town and did a test drive on freeway. Here's data he obtained. Suppose MPG for Camry is normally distributed and the population standard deviation is 2 from past experience. Provide 90%, 95%, and 99% confidence interval for Camry's MPG values. Also provide 80% confidence interval for Camry's MPG values. So basically, we have 4 calculations need to be done, 4 different confidence levels. That the process will be exactly the same, right? If you know how to deal with one confidence interval, you should be able to do, the rest of the confidence interval using the same approach. Okay. So when you look at a problem right now, we need to first identify always the population and the sample, right? The sample is pretty simple. We have 10 vehicles. That's our sample. Then what's the population? Population will be all Toyota Camry manufactured in 2015, right? That's our population. Then we're given a number 2. This is population standard deviation. Basically, standard deviation of all Camry manufactured in 2015 equal to 2. So that's our sigma, right? Then when you read through the problem, we're given sigma and we're trying to do a confidence interval. We need to do a Z confidence interval, right? Okay. So then, we can work this out. Let's write down some of the things that's useful. For example, we identified the sample as 10 vehicles. And we identify the population as all Camry manufactured in 2015, right? 2015. And then now we need to do a Z confidence interval, right? So the Z confidence interval, we need to have the construction formula as X bar plus or minus Z star times sigma over square root of n. Then we need to know the confidence level here as well. So what is the confidence level we need to use? So we have 4 different confidence levels given. We need to do 4 different calculations. We're only gonna choose one of them. We're gonna work on 80%, but any other confidence level will be the same process, right? So for example, we're gonna do 80%. And also give it sigma equal to 2, right? That's the reason we say we need to do a Z confidence interval if you look at the question, right? So sigma equal to 2. Right. So now if you look at the formula, we need to have 4 items. We need to know what X bar is. We need to know what the Z star is. We need to know what the sigma is. And we need to know what N is. Some of the things are very obvious. If you understand the sample is 10 vehicles, sample size is 10 automatic, right? Sigma, that's 2 as given. And X bar, that will be sample mean, right? So the sample is provided right here from 28.1 up to 32.6. You have 10 different MPG values for 10 vehicles. You can calculate sample mean X bar. This will go back to your chapter number 2, right? How do you find the sample mean and sample standard deviation? So sample mean, you can find it out, right? Calculate it. I skip the process of calculation here. So then x bar equal to 31.13. And the last piece of information is z star. Z star is related to confidence level, right? And the relationship is probability of z less than z star equal to 1 plus c percent, 80% divided by 2, right? If you calculate that out, that'll be 0.9, 1.8 divided by 2. So now we look backward on the z table. So you look up the z table to find a z star. The closest probability on z table is 0.8997. That's closest to 0.9. The corresponding z star will be 1.28. Okay? So then you have everything you need to do the common interval calculations. So you can plug in numbers, x bar, 31.13 plus or minus z star 1.28 times sigma equal to 2 and equal to 10. So square root of 10. And then when you calculate it, you need to make sure you calculate it with 2 times with addition and with subtraction, right? You have 2 different signs here. So for addition, you have 31.13 plus 1.28 times 2 over square root of 10. That will equal to 31.94. You can verify the number. And with subtraction, basically 31.13 minus 1.28 times 2 over square root of 10. That will be 30.32. So then we're going to write the common interval into the format of parentheses, separate by comma, small number to the left, 30.32, large number to the right, 31.94. And then lastly, we need to write a conclusion. We're going to conclude using the format we had talked about earlier, right? We have C% confidence that the average of the population is between small and large. Replace the 4 counterparts. So we're going to say we have C%, 80% confidence that the average of the population, the average MPG of population will be all cameras in 2015, right? Of all Camry in 2015, and that will be between 30.32 MPG and 31.94 MPG. Right? So that concludes, the common interval of 80% for Toyota Camry. And likewise, you can do 90%, 95%, and 99%. The only difference is for 90%, you're going to have confidence. You're going to have a z-score equal to 1.645 as provided. You don't have to go to z table, right? That's given. 95%. Z star will be 1.96, 99% Z star is 2.576, and everything else is exactly the same. Okay? And you can write different conclusions based on just different confidence levels. Questions? All right. So now, if we put all the confidence levels into axes. So for example, if we do have 90% confidence level, we concluded the population mean will be between 30.09 and 32.6 17. So this is our 90% confidence interval. Then when you have 95% confidence interval, the population mean will be between 29.89 and 32.37. So this will be your 95% confidence. And 99% confidence level, they have between 29.5 and 32.76. So this will be 99%. So for the same estimation, if you have a higher confidence level, you can see that your estimated confidence interval will be wider, right? When you have a smaller confidence level, your interval will be smaller, right? So then, we mentioned earlier, we want to maintain a higher confidence level, right? You don't want to drop your confidence level because you want people to believe in your result. But at the same time, do we want to have a smaller confidence interval or we want to have a wider confidence interval when you make any estimations? If you couldn't see that, think about the example. So if a student is transferring from out of state, they want to come to MSU to study. And the student want to know, hey, what's the average cost of living in Las Cruces if it's going to move over, right? Then compared to the two common intervals you provided, after you conducted the study, select some sample students and ask about their living costs, and then you can give them a result, right? So for example, you're going to say, hey, the average living cost of all students in the MSU is between, per month, is between $2,000 and $3,000 versus the average cost of living for all MSU students is between $2,500 versus $2,700. Which one is, more useful to the student who want to transfer? Apparently, we want to have a smaller common interval, right? We have a smaller common interval. That means your estimation is more precise, and that will help people to make a better decision, right? Instead of giving a wide range. Right? So always want to have a confidence level to be, the common interval to be small. But what you can see here, when confidence common interval gets smaller, the confidence level will drop, which we don't want, right? So keep that in mind, we're going to come back to that. So this is 80% already did in the board, the same process. Right, then this is the second animal for our attendance points, and apparently this is a camel. Okay. Right, so another practice, people's lifetime has a left-skewed distribution. A researcher wants to estimate the average lifetime of human being in the United States. So he gets a simple random sample of 100 dead people from an agency. The average age of death for the sample is 56.7 years. Suppose we know the standard deviation of the age when people die is 8.6 years. First question is, why did the researcher choose a simple random sample of 100 instead of 10? So the question is, why do we choose a large sample size, right? We use n equal to 100. Okay? So then think about the process, think about the scenario, identify the sample and the population. The sample will be the 100 dead people, their age of death, right? And then the population will be basically all human in United States, right? So this is our sample, and this is our population. And then we're given a number, the average age of death for the sample. So this is our X bar, right? We also given 8.6, and what does 8.6 is? 8.6 is the standard deviation of age when people die, and that's in general for all people. So that will be population standard deviation sigma. Okay? So apparently, if we want to do a confidence interval, this will be a Z confidence interval. If we want to try to estimate the average age of death for all human beings in the United States, there will be a Z confidence interval. Then for this problem, then why do I use sample size of 100 instead of 10? Is 10 good enough? So this would be related to earlier we talked about the conditions, right? So when you use Z confidence interval, you need to make sure central limit theorem will apply. How do I make sure central limit theorem will apply? The sample size n need to be large enough, right? So you have a larger sample size if your original population is different from normal, right? So when you look at this particular problem, what's the original variable? That will be age of death, right? Age of death for an individual, that will be continuous or discrete. Your age of death will be 70, 71 instead of 70.123, right? So that will be a discrete variable. As well as the age of death is skewed as well, right? So it's skewed and discrete. You need to make sure to have a larger sample size to apply the central limit theorem. That's the reason why we have 100 instead of 10. Okay. So next, what is the 95% common interval for people's lifetime? So basically, we need to make an estimation using Z common interval. We're estimating the lifetime of all human in the United States, right? So then we can determine it's a Z confidence interval because we're given sigma equal to 8.6, from what we saw earlier, right? So you have sigma here. Then for a Z confidence interval, the calculation will be X bar plus or minus Z star times sigma over square root of n. And for a Z confidence interval, we're going to have a confidence level, which is, in this question, we need to be doing a 95%, right? So even if I don't tell you any confidence level, we have a default to use, and that's 95% as well. So then from here, we need to have all four quantities in order to do the calculation. We need to get X bar, Z star, sigma, and n. Right? So from the problem, sample is 100 dead people, then sample size n equal to 100. Sigma is 8.6, we already know that. And the Z star is related to confidence level. So for 95%, Z star is 1.960. This will be a number you need to remember, right? And X bar is sample mean. And from the question, we're given the sample mean will be 56.7, right? So 56.7 is X bar. Then we have everything we need Just plug in numbers into the calculation. 56.7 x bar plus or minus z star 1.960 times sigma 8.6 divided by n, and is 100. And then you can have two operations, one for addition, one for subtraction. 56.7 add 1.96 times 8.6 divided by square root of 100. That will be equal to 55.01 if you calculate it. And then if you, oh, sorry, that's not right. The addition will be 58.39. And then if you use subtraction here, actually, the calculated number will be 55.01. Okay? And then the calculation part is done. I put it into the parentheses, separate by comma. So the small number to the left, large number to the right. Right? This is a z combinable. And then we concluded in terms of the context words. We write a conclusion. So we're saying we have 95% confidence that population mean, average of the population will be all human in United States is between 55.01 years and 58.39 years. Okay, so that's it. So here we use confidence. What does that 95% confidence mean? Some people like to use a word chance or probability. So instead of saying confidence, they're saying the population mean, the average age of death. Here it should be specified average age of death. The average age of death of all human in the United States has 95% of chance to be between 55.01 and 58.39 years. We don't like that statement. We don't like that statement. Okay? The reason is, think about, we have a population. Population are all human in US. Right? And we have a measure, population mean. That would be average age of death of all human in US. So is this a variable? Is this going to change? When you have a fixed population, then the average of the population will be a constant number, right? This is a fixed number. This is not a variable. It's not going to vary. So if it's not a variable, then it doesn't have a probability associated with it. It's going to be a constant number. It doesn't have a chance to be anything else, right? So think about our process. This is our population, but we're going to select 100 individuals as a sample here. And from the sample, we can calculate a confidence interval. Basically, the confidence interval is always going to be a range. In this case, it's between 55.01 and 58.39, right? So your population mean is a number we don't know. It could be either within here or it could be outside here, but it has to be one or the other, right? So the 80% chance of the population means between these numbers, that doesn't make sense. Population mean is a constant. Population mean is not going to change. Then what does that 95% confidence mean, right? So what does that confidence mean? So you think about when you draw a sample with sample size of 100, this is one of the possible samples with the same sample size, right? But if you draw samples differently, you're going to have a different 100 people in there, right? And then for this random sample, if you calculate the confidence interval, you're going to have a different confidence interval calculated because the sample mean will be different when you have different individuals in the sample. And likewise, when you go through all possible samples, each of the sample will be able to calculate a confidence interval, right? So some confidence interval will cover the true population means. Some of the confidence interval will not cover the true population means. Then out of all the possible samples, 95% of the sample will have a confidence interval cover the true population means. Okay? And that's what that confidence means. Okay? Right? So think about it, right? Try not to use a probability word in there. You will use confidence, and that confidence has a special meaning. Right. So now we're gonna have the last item we're gonna talk about in this class, in this chapter, margin of error. Okay. So if you look at the calculation of a Z confidence interval, it will be X bar plus and minus Z star times sigma over square root of n. Earlier, we mentioned from the earlier example, we want our confidence interval calculated to be narrower, right? So how do we make the estimation interval narrower? If you think about the calculation process, so basically for all the confidence intervals, you're going to have X bar right in the middle, right? And on one side, you're going to add Z star times sigma over square root of n. On the other side, you're going to subtract Z star times sigma over square root of n, right? So we define this term as margin of error. So then you have one margin of error to the right of X bar, one margin of error to the left of X bar. So your confidence interval will be basically twice as big as your margin of error, right? Then if you want to get your confidence interval narrow, all we need to do is make margin of error small because they're directly related, right? Then how do we make margin of error small? So margin of error has three things related to it: Z star, sigma, and n. Sigma is a population parameter, right? We have no control over the population parameter. Once the population is defined, the population parameter will be a fixed number. We can't change it unless you have a different definition of the population. So we can't do anything about sigma, right? And then Z star, if we get a smaller Z star, we're going to have a smaller margin of error for sure, right? So, but if you look at the relationship here, for 90%, the Z star is 1.645, 95%, 1.960, 99%, 2.576, right? So we want to get a smaller margin of error, but we need to get a smaller z-star, but the z-star is related to confidence level, right? So when you z-star gets smaller, your confidence level will drop, right? But you want to maintain your confidence level as well. You don't want to sacrifice your confidence level to get a smaller confidence interval, right? Because you want people to believe in your result. Maintaining a high confidence level is necessary. Then we can do z-star as well, right? The only thing left will be sample size n, right? So since it's on the denominator, then if you want to get a smaller margin error, we need to increase sample size n, right? So get a larger sample. Then your margin error will be smaller and your confidence interval will be narrower so that it will be more useful. Okay? So increasing your sample size is the best way to reduce the margin error. All right, so then this is it for today. In summary, we talked about inferences. We need to know what the inference is. It's a process to draw conclusions toward the population. And in general, we have two different types of inferences. One is confidence interval, in which we're trying to estimate a population parameter or population feature. And the other inference is called hypothesis test, in which we're trying to assess a claim about the population measure or population parameter. Right? So in this class, we focus on the confidence interval using Z statistics. We need to know when we're supposed to use it. We have the three conditions, but the most important is the last condition. First, we need to have a random sample. Second, sample size need to be large enough to apply central-limit theorem. And then lastly, most importantly, we need to know the population standard deviation sigma. And if that condition is met, we're able to do Z confidence interval. Right? Then how do we carry out Z confidence interval? We have a formula provided, right? So the formula will be x bar plus or minus z star times sigma over square root of n in the calculation. X bar and n, their sample size, their statistics. We're able to calculate them. And the sigma is a parameter, but that will be provided by the condition. And then lastly, z star is going to be coming out of the z table, and it's related to confidence level C%. We need to manually define the confidence level ourselves, right? In a class settings, I will give you the confidence levels. In your own research, you decide your own confidence level, okay? And if I don't give you a confidence level in any confidence interval problems, the default confidence level will be 95%, okay? So then once you have all the items you need, you have all the numbers you need, you can do the calculations, right? So when you calculate, you need to have two calculations separate, one addition, one subtraction. You can have two numbers calculated, the small number and the large number. Write them in the parentheses, right? And then don't forget, you're required to write a conclusion for every inference problem from this point on. And this is the format of writing a conclusion. And then lastly, just the margin of error, right? So the margin of error basically is just z star times sigma over square root of n. That's what margin of error is. And most of the time, we always want to have a smaller margin of error. What's the best way to get a small margin of error? You increase your sample size. Get a larger sample. And that's it. Right? But in practice, you need to understand that when you increase your sample size, you're going to actually increase your cost and time to spend to measure it. Because every one extra individual in the sample, you need to take more time to measure the values and also need to spend more money. Sometimes you need to purchase the sample individuals. Right? So that will be it. Make sure you read the videos and send me any questions that you have, and we can do discussions on Canvas. Okay. Thank you. I'm gonna stop right here.